Where's H1? Shrug your shoulders, because you don't know. Shrug your shoulders. You have no idea where H1 is. We're not going to deal with that right now. We're going to deal with H0's curve, which is that one. All right, here we go. Which distribution should we use? We're on step 6 now.
Z.
Which distribution? We got to vote for Z. Second for Z. All in favor of using the Z distribution? All opposed? Time for discussion? Of course. Why? Yes, why? Why are we using Z? Because we've learned before, even though it's binomial, we use the Z curve. We use the Z curve to stand for the binomials when the sample sizes get fairly large, like 1,000 and so forth. That's just a historical reason, YouTube world. We can also do it with the binomial. We'll see that soon. But standard practice is use the Z curve. Fantastic. So you circle Z. There are 4 distributions we'll attack by the end of this course. Z, T, you already know about those 2. Chi-square and F. I like to call chi-square the M&M distribution. That's what we'll use there. It's your Pandora's box being solved right there. And F is, well, we'll get to all those. All right, here we go. Number 7. Finally, we get done talking. We start crunching numbers. Because the question is, where does 10.1 live on this curve? We know that 12% lives here. Now, what I want to do is I want to be able to throw a ruler down this curve and figure out where 10.1 lives. But in order to do that, looking back to 243, what curve do we have to convert that to? I'll give you a hint. I gave you a program with this name. You remember? Normal stands for, remember what the stands for? Standard normal, which slaps a 0 under. That's the 0, average is 0. Remember learning that from a standard normal curve? 0 is average. 0 corresponds to 12%. The question is, what corresponds to 10.1%? So that's what the test statistic is called. The test statistic is that ruler. Now, Frankie, about an hour ago, you gave us part of it, didn't you? Because she said, I believe, if I remember correctly, you said there was a 1.9% difference between 10.1% and 12%. Did you see what she did right there? So what Frankie did, we're going to start building this test statistic right now. Here we go. Frankie said, okay, P hat, that's funny, it's got a flashback to the 80s. Frankie said, P hat, which was your sample data, minus your assumed population data of 12%, ended up being negative 1.9%, yes? Negative 1.9. Oh, you know what? Can I do that as a decimal? Is that okay if I do it as a decimal instead of a percentage? Just freaks me out. So what would that be? 1.919. Did I do that right? I think I did that right. I didn't do that right?
No, you didn't.
I did. Okay, thank you. Well, that's great and all. Except the problem is that I don't know how big that is. So what do I have to do with that to tell me how big it is? What is this? I love this. I love this. Well, actually, believe it or not, thank you for that, Frankie, thank you for that. We don't actually have to get a range. We're going to take this data that we got, the 100, 100,000, and slap it in one place on that curve. Not an entire range, but one place. We'll build the range secondarily. But what do we have to know about how big 1.9% is? It's tied to what Frankie said about the range.
Like a Z-score?
The Z... Yes. Actually, yes, let's go with that. I love that, Blake. Let's come over here real quick, if you don't mind. That wasn't where I was going, but this is perfect. Perfect. Blake mentioned a Z-score. Remember what a Z-score was? Remember Michael Phelps and Mark Spitz from 243? How you can compare those guys even 25 years apart from each other? There was this wonderful calculation called a Z-score, in which you took data that you had collected, found its difference from the average, yes? And you didn't stop there. Say it loud! What did you divide by? That was part of the central limit theorem. You divided by a standard deviation. That tells you how extremely far out you are from average. You guys are making all your conclusions about how far out you are from average. How far out you are. You don't know how far you are from average until you have a standard deviation. Then you can say, oh, it's 1 standard deviation out, or oh, it's 3 standard, or oh, it's 8 standard deviations out. Holy crap, market it. That's the idea. If it's extreme, the definition of extreme is only based on how many standard deviations out it goes. Now, Veronica, we edited this at the very end of 243 for samples. We said, okay, well let's take the sample average minus the assumed population, and then we divide it by S over root n. And that's what we're going to use here. Don't memorize these if you haven't already memorized them. We'll just keep using them. What we have to do is we have to define this for our data. And as it turns out, there's a very quick and easy calculation. You already know it. You don't remember it, and that's okay. It's simply this. It's that. It might look familiar. It might not. That's okay if it doesn't.
Calculator.
Well, yes, I would definitely use a calculator to calculate it. Do you remember that little root PQ over n from, oh, I don't know, 2 weeks ago? You can say no.
Yes.
I have one yes and a whole class of silence. It's okay. It was the standard error measure from a proportion estimate. It's the same exact one. All you've got to do is feed the values into it, and that gives you a standard deviation. Let's do it. And hell yeah, use your machines. I can do this crap in my head. Good Lord, no. You got to plug it in too. Yes, let's calculate. Yes, let's calculate. Let me see if I can get the camera looking at the right place. Yes. Natasha, we're inching in on what you were talking about. We need to know how far out that 10.1, we're getting there. We're getting there. Okay, so what I'm going to do first, if it's okay with you guys, I'm just going to calculate that root PQ over n. Just that, just the standard error. So, what's P? Well, P we're assuming is still 12%, yes?
Yeah.
That's the center of that curve over there, 12%. So 0.12 times Q, remember what Q is? The complement. Can I use the word complement instead? It's the other, it's the 12 and 8, 8.88 divided by n. Why do we divide by n? It's our sample size, and as n goes up, standard error goes down. There needs to be an inverse relationship between standard error and sample size. This controls for that. Beautiful. Divided by 1,000, boom, I get that terrible little 0.0001. But don't forget the square root. Square root's in there too, yes? So square root of all of that, we've got a standard error of just over 1%. Holy crap! I'm sorry.
So we fall outside of it with one.
Shh, you're taking one step. I love this, Frankie. Yes. You got it. The question is, where did our data land? This is going to help us answer it. Frankie, you told us it was negative 1.9%. And I go, huh? Or, huh? I don't know I don't know if I do Austin shrug, or I don't know if I celebrate, because I have no idea if 1.9% is, 2 words, statistically significant. This gives me a metric. Let me get it in focus too. This gives me a metric to actually see if it is. So now, that's the absolute difference. That's the absolute. What's the matter?
Because we can't answer in the square root.
The second answer. Answer is your little negative.
If I may, don't worry about it. Because there are built-ins that do the whole calculation for you. I don't want to derail a 244 discussion with a 65, because it's not important for you guys. We'll take care of this soon. We'll take care of this soon. Don't worry. It's a Math 95 trick, actually. Don't worry about it. This will all be done internally soon. The reason I'm doing it step by step is I needed to answer Frankie and Natasha and Blake and whoever else asked me that question about an hour ago. We now have it. 1 and some change.
That's slightly out.
Carly!
So what part is this going on for our sheet?
We're still in whatever, I forget what number we're in right now. 7. We're doing the test statistic.
Okay.
I need to know. The test statistic, by definition, is where we land on this curve. We started with this question. Where did 10.1% land? We're figuring out where it lands right now. So now, please, Mel.
I think I missed a step, but what is p-hat?
Oh, p-hat is your sample proportion. Remember your sample proportion? You had 101 people
Yes.
out of 1,000. It's the same p-hat as it was before. When you do a study, this is 101 people out of 1,000. You missed no step, my friend. That's your 10.1%, 0.101. No, and I apologize for not saying that more clearly. It's the same p-hat you're used to. Center of your confidence interval, if you will. Center of that, well, we'll come back to that too. Is that fair enough?
Yeah.
Good, thank you. So what I'm going to do now is, I'm going to divide this by that, and see what I get. So I can put that in here. negative 0.019 divided by that monstrosity, and I get about negative 1.85.
So it's a false positive.
I know. Don't be so negative, my friend. Don't be so negative. If I say negative, we'll come back to what I'm talking about right there. Hold that thought, Frankie. I love what you're saying.
It's the z-score, right?
Yes! Blake, thank you for answering you segued for me. My question is, what is that? Well, think about what we just calculated. We just took sample data minus assumed population data and divided it by a standard error. It's a z-score. That's a z-score. And guess where that goes now, friends? Guess where that goes? Where does that go? Where does negative 1.85 go? What did we start this class by asking? How far to the left 10.1 is? We now know. It's 1.85 standard deviations to the left. Ha! Negative 1.85. I called it Z, as Blake called it Z, thank you, sir. Because that's where it lives, on the Z curve. Yes, on the Z curve. So we are 1.85 standard deviations down from 0. So we now know, and I'm going to put this in parentheses because we really don't care about the 10.1%. The 10.1% needs to be transferred into a z-score in order to analyze it. Just like we did with IQ scores and pregnancy lengths and airline seats and max and going on the Tower of Terror and all those things we did in 243. We had to get all the units away and put it into a z table, same as this. So you now know negative 1.85. Standard deviations down from 0. Is the drug working? Now, Frankie went right to a false positive. She said, you've answered, I think, question 9 for us. Let's hold that thought. Based only on our data, do you think the drug is working to lower flu vaccine? What do you think right now? Well, we need, good question. Question was, what confidence? Well, let me ask you this question. What's the probability of this? So this, we landed here, yes? We landed here. Do you guys agree that it's left? It's on the left tail? Can you guys find this area that's out here? Go ahead and do that right now. Find the area to the left of negative 1.85. This requires 243. I apologize for pulling this bastard move on you. This requires 243. It's an old 243 trick from the last 2 weeks of class. Emily glares at me, it's okay. I deserve glaring for that. Yes. Use the normal! Yes? Use the normal. You can't find it. I apologize. I'm sorry. We'll do it together if you want. You want to do it together? This is probably the last time you'll ever have to use the normal, honestly. Because again, because of what Linda, when you said about the square root and the answer thing, all this stuff has a built-in in the TI. But the thing is, the TI gives you everything at once with no explanation of what it's giving you. I like going through it piece by piece, at least at the start. So, using STIN normal.
I got it.
Good. Program. STIN normal. If you guys had done, I don't think you have this. Maybe I gave it to you. Did I give it to you already? I may have. Good. STIN normal. Forward or backward problem? We remember this from 243? I got mixed reviews. Forward or backward?
Forward.
It's forwards because you have the z-scores. Backwards if you have the area. Yes? Backward will be if you had the area. It's forward. We are shading. What's the right bound? Negative 1.85. Don't put 1.85. That means that we're getting people sicker. Right? If we forget the negative sign, call it positive, means we're getting people sicker.
Yes.
Negative 1.85. Yes? Let's go draw it for us. There it is. There's our area. Looks pretty close to our curve. 3.22%. What do you think that is? What have we been calling that over the past 2 days? That has a name. We've been talking about it over the past 2 days. Look at the next.
P-value?
Yes! That is the p-value. That is the p-value. Sorry, I get excited. That is the p-value. You just think about it. What is a p-value? What does the p stand for?
Percent.
Good. Probability. Good. Give me more. It's the probability that, give me it in words, any way you can, a p-value any way you can define it. I defined it as a conditional probability in class for the past 2 days. Anything. How about when they're small versus big? How about when they're small versus big? What does a small p-value mean? What does it mean about the data you collected versus the null hypothesis you went in believing?
They don't share.
I heard statistically significantly changed, and I hear they don't share. I love both those statements. You went into this study with a null hypothesis that your vaccine wasn't going to work. That's the opposite of what you're trying to prove, and you're going to see why right now. Here's the null curve, i.e. the vaccine doesn't work curve. Where did we land on this curve? We landed on the part of the curve that makes it hard to believe that it doesn't work. It's far to the left. If the vaccine wasn't working, where should we have landed? Probably closer to the 12%, yeah? Probably closer over here. But we landed way the hell over there. That makes it hard to believe the vaccine isn't working because the p-value came in so small. Yes, that's okay. This is why we take our time through these first examples to make sure it settles in. Thank you. So Veronica, you asked a very good question. At what confidence are we operating? Right now we're operating at 95% confidence. Right now we're at 95% confidence. Is this less than 5%?
Yeah.
It is less than 5%. P-values less than 5%. What would the headline read accompanying the release of our new drug?
Flu vaccine lowers rates of flu.
Flu vaccine lowers rates! Because we're 95% confident that it doesn't not lower rates. Yeah. Even though we don't know where the other curve is. We assume it's somewhere about here, which is statistically to the left. So check this out. We just answered a couple parts of that template. Number 8, we got the p-value, yes? The p-value we just calculated, you can write it a couple different ways. You could write it as 3.22%, totally fine. You could also just say it's less than 5%. That's what you see in research articles very often, less than 5%. Very often they don't give you the p-value, they just say it's below a certain level. When you see, this goes back to Veronica's question, when you're reading those journals and it says it's less than 5%, what confidence are they at? They're at 95% confidence. Which means, what's the chance of a type 1 error? What's the chance of a false positive? By definition, 5%. We could be wrong, correct? We could be wrong. One of the questions I asked you down there is what type of error can we make? We'll get to that momentarily. Please.
Are you going to talk about the confidence interval?
Oh, sweet Jesus, yes. Blake's question from about half an hour ago. I want to wrap up with that.
Yeah. Okay,
Yeah, and why we're not doing it. Yes,
Okay.
hold that thought. Hold that thought. Now, step 9 says, circle the correct phrase and complete the conclusion based on your p-value. So first of all, you see it either appears or does not appear. So let's get some phrasing in our minds right now. When you get a small p-value, Emily, how did you phrase a small p-value earlier? You said it's something changed. So you're saying it appears something changed, yes? So when you get a small p-value, get used to saying it appears that what? It appears that the vaccine is lowering flu rates. Do you have to include the word statistically significantly? I'm going to assume you mean that. When you say the word appears, it's built in, much like it's built into that inequality sign right there. I'm assuming you mean statistically significantly lowering. So when you say the word lower in this class, I'm assuming you mean statistically significantly lower. We've been together for so long now, some of us 243, 105. I've gotten you guys so used to saying on average, over time, long run. You don't need to say it every single time. It's become part of your wiring, I hope, at this point. So, it appears as though we're lowering flu rates. Yeah. What we have just done, here's some formal talk for you. If you take other statistics courses, we have rejected the null hypothesis. This is a very, very formal phrase you might hear from time to time, not here. I mean, I just stopped saying it right now, I guess you are hearing it here. But this is called rejecting the null hypothesis. Just so you know, if you ever see that in a journal article or another textbook, rejecting the null happens when you get a small p-value. So when you get a small p-value, you can't really believe this. You have to believe this. Fair so far? What type of error could we have made? We already mentioned it, right? I think I heard it in a very, very small voice from the back. We could have made a type 1! Because we got a small p-value, which means we said it appears something changed. What kind of a test result is that if you say something changed? Positive. If you're wrong, it's a false positive. By definition, that's a type 1. Yes? You can only make a type 1 error if you say something changed. That's the way you can be wrong. You can't make a type 2 right now because you got significant results. Fair-ish, maybe. Potential. Yeah. I know, it's a lot! And think about it. Without this template, you learn all of that simultaneously. Not a good idea. Melanie, please.
Are we gonna have to use that's the normal?
No, no, sweet Jesus, no. Watch this. I'm going to do this very quickly, and we're going to do it. We're going to take our time next time. I want to answer Blake's question first, then I'm going to show you the breakdown we can get all this for. Actually, I want to answer your question second, Blake, if it's okay. This will take